Okay, hi everybody. Welcome to Eddie's dissertation talk. It's great to see such a great crowd in the middle of summer, both here in the room as well as online, and lots of old friends and new. I'll just do a very brief intro and then we leave it to Eddie. About 6 years ago, a group of us were meeting upstairs on the 5th floor, essentially brainstorming about the goal of verified AI and thinking about how formal methods could impact the emerging area of trustworthy AI. And at the time, Eddie was an enthusiastic first-year PhD student. And really, over the years, in that theme, he has grown into one of the leaders of both our group here and I would say of the broader community as well. Working with Alberto and me, he's started to build some of the key components of what we think is the design flow, emerging design flow for trustworthy AI systems and components. And so Eddie's going to tell you all about his work in this talk, and I'm happy to report that he remains as enthusiastic today as he was as a first-year student. All right, with that, over to you, Eddie.
Thank you, Sanjit. All right, I'll share my screen. Can you all see my screen?
Yeah. Yes.
Yes.
Okay. No problem.
All right, so hi, I'm Eddie. Thanks for joining. This thesis is about simulation-based testing, validation, and training of autonomous systems with probabilistic programming as an environment formalism. So let me begin. Autonomous systems are increasingly interacting with people in complex environments. For example, they're serving food at restaurants, escorting people in bustling airport, or even driving through San Francisco City to transport people. However, these are interacting with people, and if not careful, they can incur even casualties and injuries. Therefore, these systems have to be tested extensively before they're deployed in reality. And the benefits of simulation in this context is that it provides injury-free, diverse environments that are scalable, parallelizable, and inexpensive once you have the simulator. But the challenge is, in terms of simulation, how do we model and generate the increasingly complex environments of these systems? For example, how are we going to model and generate the following situations? The characteristics of these environments is that they're dynamic, it involves multiple entities and physical reactive behaviors of agents, spatial constraints. For example, in this case, the red and blue car has to be entering the intersection from the following lanes, and temporal constraints. For example, that the red car needs to enter the intersection first before the blue car proceeds in order to incur accidents. And these interactions, because can occur in variations. The red car, for example, can make a left turn, unprotected left turn in various ways. So how can we model and generate these? In this thesis, the focus is that we argue that a domain-specific probabilistic programming language is an adequate formalism to model and generate complex environments of autonomous systems. And these PPL formalism can be used for interpretable test and analysis of system in simulation, and also checking whether the failures identified in simulation can also occur in reality. And based on these findings, training a system in a targeted way. Before we delve in, I'm going to cover some background. First, our rationale as to why we're using PPL as an environment formalism. Second is a domain-specific PPL scenic, which we use throughout this thesis, and a verify toolkit to evaluate and analyze autonomous systems using scenic as an environment formalism. So first of all, why PPL as an environment formalism? Well, let me remind you, the columns over here are what you saw before, except for controllability, which I'll explain. These are the characteristics of the environment that we need to model for the autonomous systems. And on the rows are representing different formalisms that have been used. So for example, Scene graphs can generate dynamic environments, dynamic sensor data, and it's controllable, as in you can precisely control the environment using scene graphs. However, they're not reactive, meaning the sensor data that you generate are not reacting to, for example, an autopilot that you may be testing, or it doesn't model stochasticity or spatial temporal, especially the temporal constraints aspect of things. In terms of GANs, diffusion, and LLMs, they use natural English to model the environments and generate sensor data. And they can be dynamic, stochastic, and model spatial temporal constraints. But in terms of controllability, you kind of have to oftentimes prompt engineer your way through and pray that whatever you modeled in English is generated in by these techniques. And it's not reactive either. Whereas domain-specific PPLs allow you to model and generate all these constraints and models. So I'm keep saying not just PPL, but domain-specific PPL. So what does that mean? It means not only is modeling distribution, but it's modeling spatial temporal constraints, as well as domain-specific support to correctly sample environments from distributions with constraints. So for example, let's consider this badly parked car abruptly pulling into Ego's lane. In this case, let me show you an example scenic snippet where here we're modeling the spatial constraints right now, and the yellow highlighted syntax and the required statement in line 18 are modeling that. So for example, Ego is car on a lane. Let's say it's on these red lanes, and the light blue lines are representing the curves. On a visible curve, there's an intersection over the Ego's view cone, the blue dotted line and the blue line, which is highlighted as a light green area. We're gonna uniformly randomly select a point. And then next to, on the left of that spot, by 0.5 meters, we're gonna place another car. And now we have to make it badly parked, right? So we're gonna perturb it using a bad angle, which is uniformly 1 or -1, indicating left or right, with a range of 10 to 20 degrees. And then we're gonna add that constraint that it should be facing bad angle relative to that road direction, and then require that the distance from Ego to parked car is 10 to 20 meters. So these are modeling as a whole, distributions of scenes, snapshots of static environments, or which we will call abstract scene. And when we render these scenes using a simulator, you get following variety of scenes. These are concrete scenes that I'm showing. Okay, now let's model distributions of scenarios, which also involve temporal constraints. So for example, let's say for Ego car, we're gonna assign an Ego behavior, which says in tri-block by default, we're gonna follow the lane, but if there's an object within certain distance on the same lane, we're gonna brake. And if a collision actually occurs, we're gonna just terminate the scenario. And we can also add temporal constraints that Ego can see the other car at all times, things like that. And if we generate a scenario in a simulator using this program, we get a full scenario, which involves a static initial condition as well as this interactive behaviors, distributions over them. And as you can see, it's happening across different parts of the map. All right. And scenic has been applied to a variety of different domains. For example, aviation, in robotics as well, and also in reinforcement learning to model and generate dynamic, interactive, coordinated environments, as well as also in augmented reality, which I'll cover later on, to train humans. And here, in this case, all these other opponent players that you see are being generated using scenic. And lastly, verify So scenic on its own cannot actually evaluate. It's only modeling the environment. So how do we actually evaluate a system? We use verify, which takes the following inputs: a system model or its implementation, an environment model, which is modeled as a scenic program, and a property, or you can call it an evaluation metric. And how verify how it works is that using the scenic program, it extracts a mathematical representation of the distribution in the scenic program. It samples through the distributions of scenarios, and it samples a scenario, generates in simulator, and then after the simulator completes, it collects all the data of the all the agents in the scenario, and using the given property, it identifies whether the system has satisfied the property or not. There are multiple use cases. The ones that are relevant for this thesis is falsification and data augmentation. Falsification means we're intentionally trying to falsify or violate the given property in order to search for system failures. And there are other use cases such as fuzz testing, counterexample analysis, model parameter synthesis, and so on. How do we get rid of this? Does anyone know how to get rid of this? Oh, okay, never mind. Oh, there you go. All right, so thesis outline is the following, and now we're gonna enter part one, which is motivated by the following question: can we use a PPL to test the system or its components and understand why failures occur? So one of the challenges with testing autonomous systems is that, for example, they're widely adopting deep neural networks. And these are being used in different parts of the autonomous systems, which consists of perception, behavior prediction, planning, and control generally. But DNNs, deep neural networks, have been shown to be brittle and also difficult to debug. So our agenda here is, first, we look into how can we test at a system level to identify system failures, and then zoom in to component level to debug and understand, okay, what was the likely cause of those failures? So first, system level testing. What are the challenges here? First, defining the property. So how can we formally specify the multi-objectives of these systems? So if you think about self-driving cars, not only do you have to drive from people from point A to point B, but you also have to abide by the traffic rules. You need to avoid collision, and so on. These are multiple objectives with different priorities that we have to specify. So how can we do that? Second is, in terms of searching through the distribution, there are trade-offs to consider. For example, let's say if there are two different semantic features over which there are distributions assigned, and those are varying in between the red and the blue dotted lines, such that they're varying in this joint gray area. Exploitation may look like this. Once we identify a failure, we start searching in sampling scenarios, semantic feature values around that area to find more similar failure scenarios. This may help to find more failures, but there's not much diversity in the scenarios that the system is evaluated on. Whereas if we randomly explore through the distribution, we may have diverse environments, but in contrast may not find as many failures. So how do we trade off between this exploration and exploitation? And lastly, how can we parallelize the simulation to expedite the testing? And this we published to runtime verification. I'm not going to go into the detail for the time's sake, and focus more on the component level debugging, which is to understand the likely causes of failures. So what are the relevant work here so far? Well, at the time when we published this, is first, one popular approach is backpropagating through the neural networks and highlighting the input sensor data where the neural network is focusing on to check visually, is the neural network actually looking at the cat in order to say to determine it is a cat, and likewise. But the issue is this is not a scalable approach. Human has to look at each image in order and evaluate whether a neural network is functioning correctly. And then there has been semantic feature-based analysis where, as you can see, they're rotating the traffic light images, for example, and see if the perception, for example, is robust to this rotation. However, this is quite limited in expressiveness. For example, right now it's only changing a single feature variation. So how can we model as a whole much more complex environments involving multiple agents? So our proposed approach is the following. Given a scenario, a scenic program modeled by a user with nominal distributions, we're going to generate a large number of data, which, for example, in this case is RGB images. And then we're going to test, let's say, a given pre-trained perception model and see where it fails and where it works, analyze where it works successfully. And then incorporate additional constraints to the given scenario to output a failure and success scenarios in which the given pre-trained perception model fails or succeeds in. And then using that, we can systematically generate failure or success inducing sensor data. And our proposed approach is focusing on how to extract these semantic constraints for this approach. So the data generation pipeline looks like the following. Scenic program starts sampling scenes. So for this scope, we're focusing on static data. So scenes are static environments. And those a concrete sample scene may look like the following: a weather condition, position, color, model, and so on. Those are being inputted to simulator to render images or other sensor data, which are fed into the neural network to determine a binary performance. What this means is that now we can start collecting the sampled concrete scenes and the corresponding evaluation outcomes. And we can naturally pose this as a classification problem, which opens the door to use off-the-shelf explainable AI toolkits to analyze these semantic features that are responsible for failures or success. And in particular, we're using decision tree and anchor method, which was a state-of-the-art at the time. Experimental setup is that we're using a squeeze that object detector. Evaluation metric is IOU. We're testing over 4 different scenarios, and we're using a GTA 5 simulator. And the result is the following. On the right side of the table, there is a failure-inducing rules over here. We're going to add this rule into the given scenario and then generate data. But just by looking at the rules that we extracted that are responsible for the failure, in this case, we can actually start making sense of what's going on. And in this case, it's a counterintuitive explanation that perception actually fails when the vehicle is closer, not further away, as you can see from distance being less than equal to 0.84, meaning the distance from another car to ego car is less than that distance. And if we actually incorporate this, add these failure constraints into the scenario and generate the environments, generate the sensor data, indeed, we observe that the perception model is failing. So in this way, we can systematically generate failure-inducing sensor data. And when we add these constraints and then generate more data, we observe that the failure rate of the perception model dramatically increases. So this is the end of the summary of part 1, which is we start off with a system level testing and then move on to the component level debugging, which synthesizes scenic programs as an intuitive explanation as to why a given pre-trained perception model fails or succeeds. Next, we focus on the second part, which is sim to real validation, which is motivated by the following question, which is how can we validate whether the failures that we identified in simulation actually occur in reality? And why do I ask this question? Because synthetic sensor data and the real sensor data, they have discrepancies. And it's difficult to mathematically characterize this difficulty, let alone how they impact the behaviors of trained neural network models. So one naive approach, perhaps, not a naive approach, it's a go-to approach, is track testing. And in this work, we focus on using simulation to identify autopilot's failures, and then and analyzing that, generating effective test case scenarios at the track testing sites to reconstruct that would likely induce failures again. And as you saw in this video, we were able to replicate some of the failures. However, my experience from this work is that it is very labor intensive to reconstruct this scenario, and therefore is not scalable. We can't test so many in one day. And the environment background is varying in a limited way, whereas these autonomous systems are driving through complex San Francisco city with much more rich environments. So this is a time in my PhD where I realized, the things that I'm working on, it's not actually applicable, and it is frustrating. And how can I actually go about this? Track testing, I don't think track testing can be a solution for solution. So what can I do? So I start reaching out to folks in an AV industry in Silicon Valley, meet with them in San Jose, start talking with them, and through a lot of discussions, what I realized is that AV industry, they're collecting massive sensor data on road and labeling them. And those sensor data can span RGB, LiDAR, and so on. And they're actively semi-automating the labeling process, and 3D bounding boxes, segmentation, and even they provide GPS position and orientations of other objects, like the following. And then on top of that, they're actually mapping the environments where the data is being collected. For example, NewScenes, which is open source data set, they provide these detailed map information as to where each vehicle in the sensor data, which lane they're on, what is the traffic flow direction at those places, and so on. So our proposed, in this context, we propose a data-driven approach, which is once we identify, let's say, perception failures in simulation using synthetic sensor data, we encode the failures as a scenario program. And just to recall, this process is an output of our CVPR work, which are from part 1. And then given a labeled real-world training data set, we will try to identify the matching subset of the real sensor data that matches the scenario description encoded in the scenario program. And then on those data, we'll test the perception model again on those real sensor data to see that indeed is a perception model failing on the real sensor data. And the crux of this work is focusing on how that query should work. So what if the query yields an empty set in this case? It means we have identified a rare scenario, which means now we're using that rare scenario that is not reflected in the training data set. And it means now we can use that to guide simulation testing and real-world data collection. So now the problem statement is then, given a scenic program and a labeled sensor data, one data point, what is the probability? Is that label in the subset of the scenic program? Meaning, what is the probability of that label generated from the scenic program greater than 0? And what I mean by label here includes what I previously referred to as a scene information, as well as map information, like the which lane is each object on, what is the traffic flow direction, and so on. So the methodology is the following. Given a scenic program and a single label, we encode the scenic program as in a mathematical formula called satisfiability modulo theory. You don't have to know what that is for this talk. And then using the concrete values in the label and that encoding, we're gonna plug into the solver to check, is that label a match or not a match? And one thing to consider in this process challenge is that the dependencies of semantic features matter. So for example, if we compile the scenic program into an abstract syntax tree, car on road, it means, okay, the ego position, the semantic feature is on a road region. Now it's facing a road direction. So ego's heading is a road direction at, and now this blue arrow is starting to describe the dependencies, what information it needs in order to determine the road direction, right? And this across these dependencies occur across different semantic features. And so encoding these constraints into a mathematical formalism in the order of these dependency and checking is the sort of the core aspect of this work. So in the interest of time, without going too much into detail, let me skip to the experiment setup. And the hypothesis here is that do the outputs of our query algorithm correspond to the human's intuitive notion of scenario matching? So what we did here, because we don't have ground truth, we recruited 3 human participants to create the ground truth. Now, so we're using a new scenes data, 750 RGB images, and then we provided 5 different scenario descriptions to participants to manually query the sensor data. And for each participant, so for each scenario, each participant outputted their query results. And then to reduce the noise, we took an intersection of the query to get the ground truth to compare our algorithm's output results to. And we apply that across the 5 different scenarios. And the experiment results are the following. The top part is the different scenarios. The second row represents the human's output. The third row represents our algorithm. For scenario 4 and 5, both concur. Scenario 2, our algorithm actually finds 2 more data points that humans missed, which in this case was understandably difficult to find because objects are occluding at an intersection going in different direction. And for some, and this was an interesting one where a hazardous scenario where the ego car with a camera is going against the traffic to avoid a parked male car on the side. One of the humans actually completely missed this. But the limitation here is that there are errors in the label. For example, in this case, if you zoom in, the pedestrians are not actually on the road yet, but in the label, it says they are. And that's causing us to find more erroneous sensor data that are matching the scenarios. But this is the issue coming from the label, not the algorithm. So, which means our algorithm hinges on the accuracy of the labels. So the summary of part 2 is for sim-to-real validation, we first focus on test case generation for track testing. And then motivated by that work, we formulated and propose an algorithm for data-driven sim-to-real validation. And lastly, we're gonna focus on part 3, which is targeted system training, motivated by the question, how can we train autonomous systems guided by identified failures? So as a related work, previously, others have looked into using PPL. Actually, my colleagues looked into using PPL to augment data to system data using failure scenarios that they identified to train and robustify the system against the failures, as we have seen before. So what's left? So I noticed that training reinforcement learning agents, which are used in autonomous systems using PPL, was not introduced. So that's what I looked into. And looking into it, I realized RL environments are getting increasingly complex, but the support for environment modeling is lacking. And they're capturing increasingly more realistic dimensions, such as it's dynamic, physically reactive, multi-agent, stochastic, coordinated, and so on. Which, now you can kind of understand, Scenic may be able to model them. So let's see. So in this case, we use Google Research Football Simulator and a PPO algorithm And our hypothesis is, can we train an RL agent offline and online to solve difficult tasks? And for example, this is a generated scenario in the simulator where Scenic is controlling the blue opponent players, and the RL agent is being, the yellow RL agents are being trained to defend against variations of attacks. Okay, so moving on. So first, let's focus on the online training aspect. So Google Research Football provided a pre-trained RL agent, which knows how to play 11 versus 11. And in a specific scenario that they provide, the average goal difference was about close to 7. So we took this pre-trained agent and wanted to test using our domain knowledge. Okay, well, does this agent have basic field vision? Meaning, can it identify unmarked player in the on the field, quickly advance the ball to that player so that they have high chance of scoring? And in this case, we're training the blue agents for offense, and we're modeling blue teammates' behaviors in particular ways, such that they're open at the beginning, unmarked by opponent agents. And when we actually test the Google's pre-trained model here, the goal difference now drops to 0.1. So it's showing that it's not generalizing to particular situations. So to avoid the training scenario and the test scenario being the same, we came up with a mirrored version of this situation, trained further online the RL agent, fine-tuned it, and then we can see the goal difference starting to increase. So, okay, so we see that, yes, we can use Scenic in an online training fashion to improve its performance, but doesn't work all the time. So in this case, the x-axis represents names of different soccer training scenarios, and the y-axis represents the average goal difference. And let's focus on the blue column, blue bars first, which are just purely focusing on fine-tuning with online training approach. And for some of the tasks, it's not learning because the task itself is already difficult. So for those cases, we focus now on modeling stochastic policies using Scenic to generate offline demonstration data. And then now the orange bars represent pre-training the PPO algorithm on those demonstration data, and then continue training online to solve the task. And as you can see, compared to the blue bars, the orange bars are now, in general, performing better across different scenarios. Now, that's the end of part 3, and the future work is the following. Now, what I observe nowadays in different domains, such as transportation, manufacturing, and logistics, people are collecting massive amounts of data, as you see in self-driving car already. In manufacture, for example, NVIDIA is creating the digital twin and collecting massive amounts of data in simulation, and also potentially at the site in reality as well. Likewise for logistics. And these sensor data are being used to train the autonomous systems. But the question is, how, and yes, we are collecting terabytes of sensor data, and through semi-auto labeling, they are being labeled. And if I represent these terabytes of sensor data in this gray box, how much do we actually understand the contents of it? So if I look at a specific one point in that terabytes of labeled sensor data, we can see, for example, low-level, high-dimensional sensors like RGB pixels, 3D LiDAR point clouds, which may require humans to each look at and evaluate what's going on to understand its contents. But now, using the scenic query approach that I proposed, we can start looking into devising human-computer interaction tools to help people abstract terabytes of sensor data to intuitive scenario level of understanding. For example, instead of looking at a dot, now we can abstract a whole region of the terabytes of that data as, oh, this is considering unprotected left turn scenarios. And then using that, we can start reasoning about what contents of sensor data we're missing, And again, that can guide the data collection, simulation testing, and also targeted training, as you have seen before. And on the other side, I've shown you using Scenic and Simulator to test, train, and validate autonomous systems. But actually, AR and VR also offers the same simulated environment, but now on the other side, there are humans. And we can use this to start testing and training, leverage the algorithm that we've been developing, and then gearing towards human now to train them for physical skills. And I believe this can start affecting the future of works, such as healthcare, sports, manufacture, logistics, and defense. And just to show you some examples, you've seen this before, using Scenic at the top to generate tactical situations for sports. Below, and we are currently in submission process for this work, which is focusing on personalized training in AR. And this work has motivated us to also start collaborating with Stanford Medical Center to physically rehabilitate stroke patients at home using AR headsets. So in conclusion, with a domain-specific PPL as environment formalism for autonomous systems, this thesis provides a formal techniques for interpretable testing and analysis of systems in simulation, sim-to-real validation, and targeted system training. Thank you. Thank you.
Right, so are there any questions?
Yeah.
Folks in the room?
If you have any questions in the Zoom, please feel free to unmute and share. I might have.
There's a question up here.
Okay, yeah.
So I had a question. So you said at the beginning that LLMs maybe are not as amenable because they're not as interpretable and controllable because they use like natural language. But
Yeah.
have you looked into like using LLM, like communicating with LLMs using Scenic code and inputting Scenic code and outputting Scenic code so you can, because it seems like Scenic is a good way to like model the distribution in a interpretable way.
Mhm,
And LLMs are a good way to like compress like huge sources of data.
mhm.
Eddie, can you repeat the question?
Right. So the question is, for using LLMs, can we have the train LLM such that it uses now Scenic language to instead of English, natural English, to generate different types of environments, sensor data, and yes, that is definitely an interest, and I'm aware that Mirko is working on that area using LLM and Scenic. One limitation I would say though is that would require a lot of data, Scenic programs, which we don't have at this point. But yeah, but certainly it's definitely a promising direction as well. Yeah.
More questions?
More questions in Zoom?
Let me ask one of mine.
Okay.
Well, actually, there's one on Zoom actually.
Is your microphone on?
No, it's not.
Oh.
But if you can-
Okay. One question is in the chat is, could you re-explain how you might plan to label the LiDAR data in your future works section? You mean label the LiDAR data?
Sorry, I just meant like I think you talked about, oh, is it LiDAR or something about you're planning to label this in the future works, and I was just curious, like it seems like it might be, I'm not sure what you're quite labeling, you know what I mean? That's just something I wanted to get a clarification on.
Yeah, the label in this case is, for example, like we're not labeling it, we're using the labels provided in the data set to abstract so remember the Scenic query work, which is using a scenario program and the labels provided in the data set to do the matching. So we're applying the same logic here to abstract the scenario data, the scenarios, the data to scenarios. Yeah, but yeah, if you're unclear, I can help you understand after this talk. More, okay. All right, so then should I?
All right, so let me ask. With the speaker as well. Okay. Yeah, let me ask my question. You need to mute your speaker. Okay. I'll just, yeah.
Okay, Sanjay's coming.
All right. So my question is, in your querying work, right?
Yes.
ICCPS 22, you were querying static data, right?
Yes,
With a static seeding program.
right.
Okay. And obviously you wanted to extend that to dynamic data, time
Yes.
series data, and
Mhm.
dynamic scenic programs.
Yes.
So can you sketch out for us, the approach that you want to take for that?
Yeah, so I'm focusing on extending the scenic query work, which was focusing on static sensor data query to now video, a time series data. And the idea basically there roughly is to find the common formalism, right? So we have a scenic program given as we have a scenic program, and then we have a label data, which in this case may involve things like trajectories of different agents, their lane information, and so on. So there are differences in the representation right now. So finding a formalism that converting the scenic data into one formalism and then abstracting the low-level label information, time series label information into the same formalism for comparison. That is the crux of that work, and then applying the query over there. Yeah.
But let me just follow up. So you're going from scenic to generate traces, synthetic traces,
Mhm.
right? But those are still sample behaviors.
Yes. Right. So right now what we're
How do you know that the given
right.
time series data item
Yeah.
within the distribution of
Yeah.
the dynamic data?
Right. So Sanjay is asking, scenic program is in case of dynamic scenarios, is outputting basically traces of objects. How am I comparing that to the label information? So what I do actually is now I no longer compare at that level. I actually abstract scenic program into a finite state machine, and then also abstract the label into a finite state machine level, and then compare them at that level using so that's the approach. Yeah.
And you see the similar role for SMT solving there, or you're moving to a different?
Similar role for SMT solving? No, but it's gonna be still used to check the initial conditions. Yeah, the settings. Yeah. Okay.
Okay, more questions? People in the room?
Okay. Also in Zoom, feel free to ask. All right. If you have more, feel free to reach out to me afterwards. In the interest of time,
Maybe Eddie, just one question. What are you doing next?
Oh, what am I doing next? I'll be here with you, Claire.
Oh, good.
I'll be continuing as a postdoc with Sanjit and also Bjorn Hartman.
Oh, good.
Yes, now that I'm going into training people in AR and VR as well. I've been already collaborating with Bjorn. It's been great, and I'm looking forward to also collaborating with him for postdoc, potentially also with you as well, Claire, through Answer. And also, I'm also working with Zachary Pardos, who's also another professor from
Yeah.
department at UC.
Oh, that's cool. And just to say, with that stroke rehabilitation, we currently have a project with UCSF on stroke rehabilitation, not using AR/VR though. Yeah.
I'm aware. Yes.
So that might be a cool point of